We finished up talking about the cell anatomy. Now we're going to talk about the cell physiology. This is primarily how does stuff move in and out of the cell. We know that there are channels and proteins and pores, things that help allow molecules to move in and out of cells. We're going to talk about some of the specifics. Some of these methods of movement do take energy. Trying to kind of jam this stuff in and out of the cell. Other methods of movement do not take energy, and this is the difference between active, meaning energy, and passive, meaning doesn't need energy. So we're just going to simply start looking right now at some of the different ways that we can move stuff back and forth through our cell membrane. So let me just get in here. That up there. Move you guys up here. See, I like this double screen because now I can see everybody. Makes it much nicer for me. There's everyone. All right. So this is known as cell physiology, and what physiology is where we are starting to learn, excuse me, starting to learn how does the cell work? We now know the parts of the cell. How do those parts work together? So the first part of cell physiology is learning about the cell's environment. We know that cells are primarily water. We are water-based beings, and so are our cells. So where the water is, where the fluid is, if it is intracellular, now this is just terminology. That's all we're looking at right now. Intracellular, where intra means
inside.
Inside, very good, yes. Extracellular,
outside.
Outside of the cell. Interstitial means within tissue. Now, this is not talking about blood. Blood is a whole other fluid. And in fact, blood is not even physically, technically considered a fluid. It's considered to be a liquid tissue. I love that description, a liquid tissue. When we're talking about, do what?
I said that just made so much sense because now they're dividing the whole regular H2O from something totally different.
Absolutely. So this fluid, this interstitial, this is fluid that is contained within our tissues. It's what, if you think about, let's think about a specific tissue like fat tissue. Oh my goodness, adipose tissue looks like a sea sponge. It has these giant voids, and these voids are used as storage units. And depending on what they're storing, if they're storing a lot of fluid, that's where I think every single person in here has, let me think, been on a long car ride and you get out of the car, your feet are all swollen up. Or you've been on a long flight, a long plane ride, you get off the plane, your feet and your legs are all swollen. Well, why is that? It's because the fluid has settled to the lowest level and it has filled up those little areas within the adipose, and that's interstitial. Sorry, I have something in my eye. And no, it's not my finger.
Would that be what happens like when you get pregnant and you get a bunch of fluid built up? Is that the same thing, kind of fluid?
Yeah, that's literally exactly what I'm talking about. That is interstitial. And for whatever reason that's happening. And in fact, when we get an over accumulation, Lauren, of fluid, you get pregnant, you get the cankles, your feet look like little piggy sausages. That is now called edema. And what edema is where the tissue is actually swelling because of the fluid accumulation. So that's a whole condition unto itself, is edema, which is just an increase in that fluid to where the tissue is actually beginning to swell. So these three terms right here, I want my, there we go. These three terms right here are just saying, where are we looking at? The intracellular is fluid inside the cell. The extracellular is fluid outside the cell. And interstitial fluid is fluid that is contained within the tissue. This is all review, you guys. This is all review. Just making sure everyone's on the bus before we move on. So we know that ions are an atom that have gained or lost an electron. Remember, changing the charge. If we gain an electron, what happens to our charge?
We're negative.
Yeah, because remember, we think about our electrons as negative feelings. So if I get lots of negative feelings, I turn negative. If I get rid of negative feelings, I turn positive. And if I am positive, I am referred to as a cation. And if I am negative, I am referred to as an anion. Is everybody okay with these concepts?
Yes, ma'am.
Why is all of this important? Well, it actually is on a technical level. These ions, sometimes we also refer to them as electrolytes. These are super important to make sure that we are maintaining in our patient. Things like sodium, chloride, potassium, and calcium, these are 4 major electrolytes that have to be in balance in order for our animal to be healthy. And these are some major electrolytes that sometimes go out of balance. And that's why we use the IV fluids that we use. One of the major IV fluids that we use is called NaCl, which is sodium chloride. So everything we've done up till now, I know have been kind of an abstract concept. It is, though, going to be used in veterinary medicine. All right, we know that cells have this membrane, and this membrane separates the inside environment from the outside environment. However, we have stuff that has to pass through. We have amino acids, hormones, gases. We need fluid to be able to move in and out to maintain the pressure. We want to have homeostasis. Our cells, I think we talked a little last week, cells are pooping. Our cells are pooping, and we got to get that poop out of the cell. And our cells are also creating things. And these things, we talked specifically about the creation of proteins with the ribosome. And then those proteins are sent via a transport vesicle to the Golgi apparatus, which are then repackaged, sent to the environment. Well, if I can't get them past the cell membrane, there's no point in doing any of that. So that's what we're talking about now, is simply moving stuff either into the cell or out of the cell. And these processes could be passive, meaning they do not require energy, or they could be active, meaning that they do require energy in the form of ATP. ATP, remember, is adenosine triphosphate. We have 3 little phosphorus molecules. We break the bond, release some energy. We now have diphosphate. Reform the bond, break the bond, reform the bond. And we do that over and over, and every time we break that bond, turning ATP into ADP, we release a little bit of energy. Now, cell membranes, they're incredibly complex. I think we can all agree on that. They could be impermeable, meaning not passable to some substances, and freely permeable to others, and still yet selectively permeable, meaning some can come in, but some cannot. Why do I have this picture up here? This is a wonderful visual representation of a cell membrane. Does anybody know what is going on right now in this
Red
picture?
Rover, let whoever come over.
Red Rover, let someone come over. And for those of you who do, if you've been living under a rock for your whole life, what happens then is the person who's been called runs like gangbusters towards this group who have all of their hands. If he breaks through, he gets to choose someone and join back his group. But if he does not break through, they get to keep him. And so it's just a little children's game, but this is a great representation visually of a cell membrane. So if this group is the cell membrane, and this guy is something trying to get in through the cell membrane, so we can see if he breaks through, that would mean it was permeable. Permeable meaning to pass. If he does not break through, it is impermeable. And then selective, they may allow some kids pass through, and I'm willing to bet, okay, I form these scenarios in my head. This guy's going to be selectively permeable, meaning some molecules are easier to pass than others because he is aiming right here for the weakest link. This guy is standing on one foot. He is not ready. He is not ready to do anything. And this guy is like, I see that. Pew. And he's going to go flying right through there. The children are getting hurt right now. I can see within 3 seconds, children are getting hurt. But this is, again, just a nice mental representation. Impermeable, meaning cannot pass. Freely permeable, passes very easily. Selectively permeable, only some can get through. So let's first talk about passive. Passive means no energy required. And we have 4 passive processes. Diffusion, and I'm willing to bet some of you have diffusion transport processes happening in your homes right now, and you don't even know what I'm talking about. That's okay, I'll explain. We have facilitated diffusion. Well, what does the word facilitated mean? Does anyone know?
We have to aid it.
Yeah, it needs help. We have to aid it. We have osmosis and we have filtration. So we're just going to go through the definitions of these 4 different transport processes. All right, let's talk about diffusion. Does anybody have, let me grab one so that you can see what I'm talking about. Oof. Pull it out of my own wall. Oh, I gotta put a new thing in there. This is one of those, this one's from what, Bath and Body Works. It has a little smelly thing. You plug it in, the smelly thing comes out here, and it fills up the room with a lovely smell. Does anyone happen to know, what this thing is called?
Diffuser.
Diffuser. Oil diffuser.
This is a diffuser. That's what we're talking about, is diffusion. So basically what happens with diffusion is we have an area of high concentration and an area of low concentration. And the molecules are going to move from high to low. So if you think about it, This is the this is very concentrated. Oh Lord, if you've ever accidentally taken a whiff directly out of the bottle, ooh, oh my God, that'll clear your sinuses like crazy. The room is low concentration. So what's happening is ooh, that's very sticky. Ew, sorry, touched that. Let's just wipe that off a little bit. So as it's coming out of the holes right here, that is super high concentration. You ever plug in a new smell and stand right beside it? Oh, holy smokes, it's overwhelming. Especially if it's a new smell that you're not used to. Oh, sometimes it's terrible. But then it gradually fills up the room. The smell gets less and less. That's diffusion. We move from an area of very high to very low. Another mental image that I use for diffusion is pre-COVID. Everything has to be, God, what? Everything has to be stated pre or post-COVID. That's where we are right now in our lives. Pre-COVID, we go and see my Texans be victorious. Did anyone watch that game yesterday against the Patriots? Heck yeah. It was not the prettiest of games, but it was a win. A win is a win, and I'll take it. Second half, my boys actually showed up to play. It was a beautiful thing. I haven't seen JJ do his finger move in quite some time.
Man, JJ did those 4 swats. My God.
Oh, he was old JJ. He was not down.
I think he got tired of everything going on. He got tired of all that after they lost the coach. He said it's time to buckle up.
He said it's time to show up. Okay, so I don't know if any of you, it doesn't matter if it's football. I'm using football. The point is you go to the game. You go to the concert. You go to the show. And when that concert or that show or the game is finished, we've all had this experience where you have 30,000 people trying to leave at the same time out of 10 exits. And you're moving and you're like shoulder to shoulder, and like the crowd is literally just moving you along. And so the high concentration of people is in the building, which now is mimicking, let's say, our cell. Moving to the parking lot, which had a low concentration of people. That's a great mental image of diffusion and the concentration gradient, moving from high to low. Now, some of the factors that are going to influence the movement, obviously the molecular size, the molecule that's trying to move. Smaller molecules move through easier. Fat solubility. Fats pass through fats, and we now know that our cell membrane is lipid. Molecular charge. Is it a cation? Is it an anion? And the temperature. Things move faster in a hot environment. And again, your concert or your game, holy smokes, it gets up to about 1,078 degrees in the crowd. And everybody smells like BO and beer. I'm sorry, it's disgusting. And you definitely want to get out as quickly as possible. That's temperature. The hotter the temperature, the faster stuff is going to move. So the big thing is this concentration gradient. Now, when I talk about a spectrum, all I'm referring to is what's the difference. I have high concentration and low concentration. What's the difference between the two? That's going to determine how fast stuff moves. Look at this slide. High concentration, low concentration. The difference between the two determines how fast we slide. If you compare this slide to this slide, this is like the most pitiful slide on the playground. because there's not a whole lot of difference between the high and the low. Do you see that if there's not a lot of difference, my molecules are going to move much slower? This slide is almost one of those where you got to like push yourself along on it, like a little baby kitty slide. This one, however, the molecules are going to move very, very quickly. So if there is a great difference between the high and the low, my molecules are going to move faster. If there is not any difference between the high and the low, or very little difference, my molecules are going to move much slower. Does that concentration gradient make sense to everybody? Is anybody not on the bus? Do I need to go back and re-explain this at all?
Can you do it for me, please?
Absolutely. So when we're talking about concentration gradient, we're referring to the difference between the highest and the lowest concentration. So if this slide right here represents my gradient, here I have my high concentration and my low concentration, and my molecules are going to move much faster than this slide. So there's my high and my low, and my molecules are going to move much slower. Let's take right now, let's do our example again of the Texans game or a concert, what have you. So back in pre-COVID land, it was really kind of an event to go to a Texans game. We used to try and get to at least one Texans game a year. And there's, again, I don't know how much NRG holds. We'll say it's sold out. I don't know how many people that is. But everybody's trying to leave at once. And everyone's trying to leave very quickly because it's not comfortable. That's a very high concentration. There's a lot of people inside the stadium. There's nobody outside of the stadium. And we're moving very quickly from high to low. Think about after the game now, when they're only seating at 20%. There's nobody in that stadium. So I'm going to be meandering along. I might stop and get a hot dog, maybe go over here and look at a t-shirt. I am not in a huge hurry. So the lower the concentration, the slower the movement. The higher the concentration, the faster the movement. Same as here. Big difference fast, little difference slow. Does that make sense?
I got it now.
Got it.
That was a good one. That was a good way to, I got it now.
Here is a visual representation of this. So if we say that the smell coming out of this is the little red diamonds here. So I have my diffuser and I have plugged it into the wall right here. So this is very high concentration of smell. And as it starts to move its way through the room until it has done what? Diffused. And now has equal representation throughout. That's diffusion. Here's another kind of funny example of her diffusion. Yeah, so when you do a toot and it is super smelly around you, and then a few minutes later it hits your significant other, and then it fills up the whole room, that's diffusion. All right, so facilitated diffusion. Diffusion, we're still using the concentration gradient. We're still moving from high to low. But now we need some help. Now we need someone to give us a hand to get from high to low. We have a carrier molecule. The mental image that I use for this, so my significant other and I have decided we're at the game. It's pre-COVID. The game has let out. We have been victorious. Huzzah. And we are moving from the high concentration of people to the low concentration of the parking lot. And I have had a few too many burrs and I need a bit of help. So he puts me on his back and gives me piggyback ride and gets me out. We're still moving with the gradient from high to low, but now he is acting like a protein that is helping me move with that gradient. That's facilitated diffusion. Here I have my phospholipid bilayer moving from high to low. That's just this picture's representation. The gradient happens to be high here and low here. So I'm moving, and here I have a protein that is helping this molecule move with the gradient from high to low. So this guy is the piggybacker helping to move this molecule. Why might I need something to help me? Maybe the molecule is too big. Look how big this molecule is in this picture representation. If I tried to force that through this membrane, I'm going to rip the membrane and I'm going to kill the cell. So I need to have something that was going to help, but diffusion, meaning I'm still going with the concentration gradient. Is everybody okay so far?
I just had a quick question.
Sure thing.
I wanted to confirm for my notes. So high concentration is faster? Is that what you said?
Okay, well, not necessarily. It depends on the difference. If there's a big difference between here's high and low, fast drop. If here's the difference, high and low, slow drop. So the greater the difference, the faster the movement.
Thank you.
So here's just another, for my little visual learners, I know some of you, you need to get that picture in your head, just like me. So in this case, we are moving from the top of the stairs to the bottom, right? High to low. And we have a carrier protein facilitating or helping our molecule to move with the gradient.
Bing.
Does that work?
Yes, ma'am.
All right, so the third passive level, excuse me, the third passive method, rather, of movement is osmosis. Osmosis is the movement of water. So with our diffusion and our facilitated diffusion, we were moving molecules. Yeah, I love everyone. If you want to look at the chat, Stanley has a fabulous, fabulous other analogy for the gradient is rolling balls down the hill. Or if you, if you're a little kid, hey, Stanley, ever do this? And you get at the top of a high hill and you yourself just roll down?
Yes, I did it at my aunt's old neighborhood. She lives like by a little hill, and me and my cousins will go down the hill, rolling down it.
Yeah, where you just roll, and the faster, the higher the hill, the faster you go. And then you
Yes.
usually hit the rock at the bottom. So it was always great. All right. Osmosis is movement, but now we're talking about water. We're not talking about molecules, we're talking about water. And so when we're talking about osmosis, the body wants everything to be even Steven. That's kind of the whole point, is even Stevenness. Yeah, I'm making that a word, even Stevenness. Wants everything to be nice and equal. So when we are looking at osmosis, if I have an area of concentrated and an area of not concentrated, and I want these two areas to be even Steven, I need to move water from where to make them equal. I have not concentrated or dilute, and concentrated. Which way do I need to move the fluid to make these two things equal?
Dilute.
I need to move from dilute to concentrated because remember, we're moving fluid. Because I know some of you are like, well, why aren't we just moving stuff from concentrated to dilute? That would be great if we were moving molecules, but we're not. We are moving fluid. So if you think, I have 2 glasses of water, and one of them I have poured half a cup of salt, and I can magically allow stuff to pass between these 2 glasses. And I want this to have them be equal. So I'm going to be moving water from the dilute in order to dilute out the concentrated. Somebody just got a brain. Rachel, did you just get it?
I did. I never understood how it worked. And then you're explaining osmosis. I was like, oh, so that's how our thing works.
That is how the thing works. Is that
Light bulb just went on. Bam. You got a
I
lot of
love
us.
that. I love that. That's osmosis. That's osmosis. We have the movement of fluid. Remember, the whole point behind osmosis is the fluid, not the molecules. I am making the dilution equal by moving fluid to dilute out the concentrated until the 2 are equal. So if
Like when you buy the dish soap. You buy dish soap too concentrated, it's too soap's too thick, you add some water to it to kind of dilute it out.
100%. Here I have, excuse me, a high concentration. I move the until the concentration is equal. So obviously the volume is going to increase on the one where I am got a lot of concentration, because why? I'm moving fluid into that area, increasing the volume. So now, even though one has increased and one has decreased volume, the concentration between the 2 are equal. That's osmosis.
So what's the concept of reverse osmosis then? 'Cause
So
I've heard of-
so reverse osmosis is exactly what it sounds like. Instead of moving from low to high concentration to make them equal, it's moving fluid from high to low to further concentrate this area.
Okay, I just wanted to make sure I got that down correctly and not
Yeah.
just assume.
No, you are absolutely right. Another great example, I don't remember who it was that was asking about swollen ankles. I think, Lauren, was it you? Okay, so when you eat a lot of salt, and in fact, if you have high blood pressure, you know how they say you should be on like a salt-restricted diet? Well, here's why.
Salt makes you retain water.
But why does salt make you retain water?
That's where you come in. Help me out.
Okay, so I'm eating all of the salty things, eating every of the salty things. And the concentration of salt has increased in me. So my body has to retain what to dilute out the salt?
Water. So it
Bam.
causes swelling.
Bing, light bulb again.
So if I'm retaining a lot of water, do you see how that would cause my blood pressure to go up even more? And I now have so much fluid that it would start leaking out into my tissues, causing swelling of the tissues.
And so now there's another process forward. Once you start releasing, when you're taking, it's releasing through the pores.
Yeah,
The sweat.
that's absolutely.
Okay.
Could that also be a reason why when you're pregnant you crave salty stuff because you need to get more water, or how does that?
Yeah, it could
Okay.
be. There's a lot of research being done because salt is what causes your body to hang on to water, right? That's the whole premise behind it. Salt makes you hang on to water because it's trying to what? Dilute it out. But isn't the entire premise of our entire bodies to hang on to water? Every organ function in our body is set up to hang on to water. That's how your kidneys work. Your kidneys have an area in them that is super, super salty. And so guess what happens? Fluid leaves the blood that is being filtered and goes into the tissue and is recycled. And so the more salty you are, the more water you hang on to, because we're trying to get into the land of even Stevenness.
Oh my God, that makes so much sense because I love salty stuff, and when I was pregnant it was worse, and I had so much fluid build up like at the end of it. It makes sense.
Yeah,
That's where them cankles started coming in.
here's another, just because I love these light bulbs. So you go to the no, I'm not talking like the club. I'm talking you just go to a pub. You go to the pub. What's in a bowl on the bar of the pub?
Peanuts.
And peanuts are
Shelled.
They're salty.
they're
Salty.
salty. They're salty.
Full of salt.
It's okay, Rach. It's okay. It's Monday. Peanuts are salty. And if you increase the concentration of salt in your body, what is going to happen to you?
You're gonna get
Get more
thirsty.
thirsty.
And then you buy more beers.
Oh.
And the more burpers you drink, the more you're urinating. You are now dehydrating. Your body now craves salt to try and retain that fluid that you're losing. So it's kind of double.
So they're sneaky and they try to make you dehydrated so you'll drink more, so you'll drink more.
Yes. Gabs, 100%. Yes. Yes. All right. So if the concentration on the inside of the cell, I actually want my, what do I want? I want my, where's my pen? All right. So I have my cell. If the concentration is the same on the inside and the same on the outside, we say that it is isotonic. Guys, this is just med term. Yes, salt is super bad with dogs and cats and kidney failure. Kaylee, salt is bad for anyone in kidney failure, because when we get into kidney function, it'll make a lot of sense. But yes, 100%. All right, so if the pressure is the same on the inside as the outside, do I have promotion of movement anywhere? No. I don't need to move anything anywhere. That's ISO. ISO means the same. If, hang on here. Oh man, I didn't mean to do that. If the outside is more, or I'm sorry, less concentrated than the inside. So the inside of the cell is more concentrated than the outside. These, do you see the word hypo? What does hypo mean?
Oh, low.
Low.
Low, low.
Lower than.
these are referring to always
The
the
outside.
outside. So hypo means the outside is lower than the inside. So the inside of the cell is more concentrated. Tell me, how is fluid going to move if the inside of my cell is more concentrated than the outside?
It's gonna move slower.
What do I have to do to make the inside and the outside equal?
You got osmosis.
Mm-hmm.
I got an osmosis in what direction?
You
You want
want
to suck it in.
I
Yeah,
wanna
you
s-
want
I want to suck it in
Mm.
because I want to dilute this to make it the same concentration. Does that make sense? So now when I'm looking, I lost my mouse. I hate that. Now, oh, that was cool looking. Now I have hypertonic. And remember, these are referring always to the outside of the cell. Hyper means now the outside of the cell is more concentrated than the inside. Now how am I moving fluid?
You're pushing it out.
Yeah. Hey, one quick thing. I don't know if you guys know this. Do you guys know that you can draw on my PowerPoints?
Oh no.
Yes.
Hold on. The annotations or whatever at the top.
I don't know. Rachel,
Or
how
you-
did yeah, you guys can
Guys.
draw. You guys, there are little stamps, little heart stamp. Look at that. Someone just drew. I don't know who's drawing right now. Hey,
I am
look,
so jealous. I'm jealous.
look at you guys. Look, someone found the heart and the star
Sorry.
Oh my
stamps.
God.
Sorry, but yeah, that's cool.
How do you do that, Miss Huff?
I don't know.
Oh.
I don't know.
It gives you an option.
I
It even
honestly
has-
don't.
It even has
I-
a little bar for emotion.
Oh, I
Joseph
see
found the
reactions.
letters.
Yeah, the
Oh, I see.
reactions, all that good
Oh,
stuff.
look.
Okay.
Look at Eric got fancy. Look at you guys go.
Look at Joseph.
Chloe. All right. Yeah, how fun is that? You guys can draw all over this as long as it's appropriate, okay? Let's keep it appropriate. Let's keep it appropriate. All right. So here's what I want you to do. We now have on my cells an area of low concentration inside the cell and an area of high concentration outside of the cell. Somebody draw an arrow and show me how our fluid is going to move to dilute.
It's gonna go. All right.
We're gonna move, well, we're actually going to, so if we were moving the molecules, you're absolutely right, because this moving from here to here, if I was moving the molecules, that would be diffusion. But I'm
Okay.
moving the liquid, I want to dilute this.
Oh, okay.
You see how I have to
Yeah.
move the liquid this way.
I'll move that
So
way. Okay.
concentration gradient, you are absolutely right. And if I was moving the molecules, you were absolutely correct. I'm moving from high to low. In this
Okay.
case, though, I am moving the fluid. I need to dilute
Okay. So move.
this. So I have to move the fluid to dilute it this way. So I think last week we were talking a little bit about like when you take gummy worms and you set them into a clear adult beverage.
Yep.
Those gummy worms compared to the beverage, are,
Isn't it hypo?
they are hypo, meaning that we are, so the inside of the cell is more concentrated than the outside. The gummy worms are hypotonic in comparison to the vodka, which means I promote movement of the fluid into the gummy worm, causing it to
Swell up.
swell up.
So it soaks it up and then sponges.
Yes, because of osmosis. We are moving the fluid based on these osmosis premises.
I remember learning this in biology freshman year, and we had to take like an egg and put it in water, and that was isotonic, and then we had to put it in vinegar and maple syrup, and it was like growing and shrinking. It was so nasty.
Yeah, that's disgusting. I think actually Ms. Regalia, if I'm not mistaken, does a similar experiment but with gummy worms. And she uses a hypo, and an isotonic solution. And the gummies will get bigger, smaller, or stay the same based on the solution that they're in.
So this is also part of chemical reactions as well, huh?
It is, although right now we're just moving fluid. And where this is really important is when, now I know this is kind of an abstract concept, but this is super important when we start discussing and choosing things like IV fluids. I have some fluids that are going to promote the movement of fluid into the cell, and some that are going to promote the movement of fluid out of the cell. If my cells have too much pressure, I want to relieve that pressure. So I want to give them an IV fluid that's going to promote the movement out of the cell. And that's going to be super important, because if I give them a wrong one and I promote the movement into a cell that's already under high pressure, what's going to happen? That's not good. All right. I'm going to erase your, oh no, I can't erase. I can't.
Maybe we have to go individually.
Maybe they have to
our
erase
own.
it. Maybe they have to erase it
yeah, I
themselves.
think you guys have to erase your own, because I don't have the option to
Yeah,
erase
like
it.
I pressed clear and it took out what
Oh
I
yeah,
had.
everybody's taking it off.
There you go. Although, honestly, you guys, not just today, but going forward, if we're doing Zoom and classroom, and you have a question and you're like, nobody's listening to me, just write it on the slide. Joseph says it will not erase. That's fine, Joseph. You just stay on there, darling. You just will be our little rock star on the slides. All right. I don't know who's. Oh, there you go. You got it. Whose hearts are these? Who did the heart? Oh, there we go.
Out.
Don't know. All right. When we're talking about biology and we're discussing the pressure of blood and the pressure of the tissue, all right? So we're now the pressure inside the blood vessel. Oops. Inside the blood vessel, we have the pressure, and out here, the tissue. So you can now see, based on the premises that we just discussed, I can promote the movement of fluid from the tissue into the blood, or I can promote the movement of fluid from the blood to the tissue. That's exactly what we were just talking about with salt. And when I move fluid into the tissue does what? It swells up. And so this difference in the pressure has a medical term, and that medical term is known as oncotic. That's how you say that word, oncotic pressure. That's just simply the difference of the pressure in the blood and the difference of the pressure in the tissue. Oncotic. All we're looking at is terminology. All right, so the fourth and final passive is filtration. So where we have filtration is, one example is when your heart beats, right? When your heart beats, we got our beating heart right here. When your lower chambers, otherwise known as the ventricles, when your ventricles contract, they sploosh. I love that word, sploosh. They sploosh blood into your blood vessels. The splooshing of the blood causes your blood vessels to expand. And then when your ventricles relax, they contract. If you feel your pulse, when you feel the blood vessel push against your finger, that's because your heart has contracted, you're feeling a sploosh. Another great example of filtration is the coffee maker. Now, I'm not talking about the fancy Keurigs. I'm talking about your good old-fashioned Mr. Coffee.
The ones that take a filter.
The ones that take a what? A filter.
A filter.
Okay, now some of you are looking at me like, what the hell is a Mr. Coffee? And to you, I am going to share a mental image with you. Are you ready? Let's see who is psychically connected to me right now. Let's see who's psychically connected. I'm thinking of a finger.
Middle.
I did not say that. You said that.
But I knew what you were thinking.
You said that.
I said it. You were thinking it.
I don't like coffee either, Stanley. This is my coffee right here. But my significant other does like coffee. So I have coffee maker. What do you have to do? You put the filter in, you put the coffee in, you put the water in. The water runs through the filter, pushing the coffee through, giving you a lovely coffee, a cup of coffee. So the
and there's
liquid,
also that, and that the grinds still stay there. So that's some of that's the stuff that stays in the cell. Only selective come out.
right. So the liquid is pushed through the membrane, which is the filter. The pressure is higher on one side than the other. So where the water is coming out of the coffee maker. So here I have my coffee maker. Here I have my filter. Here I have my coffee grounds. And the water is pouring into the filter. So my concentration is higher here. I am drip, 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 moving the fluid through the filter to the other side. That's filtration.
That is the most best example. If you don't get it, I don't know who won't.
Is everybody okay with that analogy? So the four, just to go back and review for a minute, the 4 methods of passive movement. Passive meaning no energy needed. We had diffusion. We're moving molecules from a high to a low concentration, and the difference between that concentration is known as the gradient. We had facilitated diffusion, where we're still moving from high to low, but now we have a helper. We have some sort of protein facilitating or helping the movement. We have osmosis, which is now the movement of fluid. But the movement of fluid is moving opposite. It's moving from low to high because we are diluting out and trying to equalize the concentrations. Filtration is simply the movement of fluid through a membrane. Those are the 4 passive movements. No energy required. Do I need to go back and review any of those passive movements? Is everybody on the bus right now?
Okay, I just have one question. On your 4 steps, it was diffusion, facilitated osmosis, and what was the last one?
Filtration.
Filtration.
One we're on.
Thank you.
You got it. All right, so active movement is movement that is going to require energy. Some molecules can't enter or exit the cell. Maybe they're not fat soluble. We know that water soluble things are definitely going to require energy. If they're too big, humongous molecules, super duper going to need energy to move in and out of the cell. And if they're on the wrong side, so if I am moving against the gradient, instead of going down the slide, I'm trying to climb up the slide. That's what I'm saying when I'm saying I'm on the wrong side of the gradient. My molecule is moving against the crowd. So these all require energy. So the first one, here are active transport process. We have the symport, where things are moved. Sim meaning what? The same. So if substances are moving in the same direction, it is symport. If they are moving in an opposite direction, they are antiport. And some of our transports, this is just terminology, guys. Where is stuff moving if I have endocytosis?
Inside.
Inside.
Inside what?
Inside the body.
Inside the
cell.
I'm moving into the cell. And if I am moving things in the exocytosis,
You're moving things
Outside
outside the cell.
Outside.
I'm moving stuff out. To bring stuff into the cell, now I need you guys to visualize your little cell like a little person. I've got some processes here. Phagocytosis. Does anyone remember what the medical
Eat.
term? To eat. My
Eat.
cell is eating. Burr, burr, burr. I'm eating my Fruit Loops. I'm eating my cereal. That would be endocytosis, taking stuff into me. I am now the cell. But phagocytosis means I am taking stuff into myself. Phago, though, would tell you it's a solid particle. Cereal, I'm eating it. Pinocytosis is all, I'm still taking stuff in, right? All of these three are taking stuff into a cell. Pinocytosis.
Oh, Pinot, like Pinot
It
Noir.
would be like liquid.
I was just going to say that. Pinot means to take in a liquid, like a Pinot Grigio or a Pinot Noir. So when you think Pinot, you're going to think of that lovely wine glass. Diet Coke. Receptor mediated means that it has to have a key in order to get in. It can't just willy-nilly. This one, you got to have the code. This
I
one,
got the right tool to get in.
it's got to have the right tool to get in. It's got to have the receptor. Exocytosis is where I have eaten, I drank, I took in the receptor mediated, and now I got to go poop or I got to go pee. And I am now moving stuff out of me, the cell. So this is just a picture showing that active transport. And again, our molecules can move against the gradient. And what that means is I have high concentration, low concentration. We know if I'm moving with the gradient, it would be in this direction. If I move against the gradient, it would be this direction. So if we're talking about moving against the gradient, let me give you another analogy. So we've left the Texans game Everybody is inside the stadium moving to the parking lot. We're moving from a high to a low concentration. And I am moving with the crowd. That does not take any energy. And suddenly I go, oh no, oh gosh, I left my t-shirt in the chair and it cost $280 and I should go back and see if it's still there. So I now have to turn around and I got to go against the crowd. Everybody in here has had to do that at some point in their life. Move against the crowd. I am moving now against the concentration gradient, and I am having to use energy. So with the gradient is passive, against the gradient is active. Here's endocytosis, moving things into our cell. If the cell is taking in solid material, it is phago, and eating. If it is liquid, pino. And if it is receptor mediated, it means that it has to have the code. It has to have the key. Those are the three ways that we can bring stuff into our cell. Here's a picture for you little visual learners. I have a solid particle right here on the outside of my cell. This solid particle comes and binds with the cell membrane, and then the cell membrane pinches off, and we have brought in the solid material into the cell. Endocytosis via phagocytosis. Endocytosis, I've just brought something into the cell. Phagocytosis tells me it was a solid particle. Pinot Grigio, Pinot Noir. Here I have my liquid, exact same premise. It comes down, it joins up with my cell membrane pinches off, creates this little vesicle, and has now moved the liquid into the cell. And I know it's liquid because of Pinot, and it's moving it into the cell because of endo. And then finally, we have our receptor mediated. So here on my cell membrane, do you see these little green guys right here? They only accept the star-shaped molecules, and that's it. So if any of these little blue squares or the little big red jelly beans, if any of those come down and try and bind, it's not the right key.
I'm just going to say you can't pass.
You can't pass. The only ones that can come in this area are the ones that will bind. And in this case, it is the little stars. And so only the stars are going to be allowed, and only the stars are brought in. That's receptor mediated. You have to have the key for the receptor in order to activate entrance into the cell. Is everybody okay with endocytosis? And then, of course, we have what comes in, must go out. And yes, I Google image search, dog taking a dump on a lawn. Because now the dog is representing the cell and he's pooping. But it's not just waste, obviously. I mean, we're creating things. We have a symphony inside this cell that needs to get out into the environment. And so this is how we get that creative stuff out. Exact same way, but in the opposite direction. Instead of having our stuff come in, bind with our cell membrane, pinch it off, and form a vesicle, we're doing the exact same thing in reverse. We have whatever it is that needs to be secreted, symphony, proteins, waste. Now we have it in our vesicle. It comes and binds with our cell membrane, and then it releases and jettisons all of this out of the cell. That's exo, moving it out. All right, so time flies when we are having fun. So that is the method with which we move things in and out of the cells. What we are going to start discussing tomorrow is how do cells replicate? How does this cell make an exact copy of itself? Because as we know, cells don't live forever. They are not immortal. So if I have a cell that has lived his life, he's had a good life. He's had a good life. But now it's time for him to go into retirement. He needs a young whippersnapper cell to come in and take his place to do his job. So how do we do that? Stanley, don't cry, sweetheart. I am going to make you, here's my promise to you, I am going to make you not only understand, but like the concept of mitosis. Yeah, I'm doing it. Stanley with the kitten on his head. Stanley's giving himself a CAT scan. Sometimes it's just for me, and that's okay. Come on.
No, I'm
Come
cracking
on.
up. I'm cracking up too. I was just on mute.
That was funny. Come on. All right. So we're going to start with mitosis tomorrow. And Stanley, I got you, man. You know that. I got you. No man, no person left behind. No person left behind. So let me get this